Okay, so welcome everyone for the last session of today, and it will be Yael Roshman from Tel Aviv telling us about thermodynamic significance of effective temperatures in driven and active systems.
Thank you, and thank the organizers for inviting me here for my first time in India. Okay, so we've already had a chance to hear some fantastic talks today, and I think this goes more or less in line of what we've heard. I would try to give you some of my perspective of where I'm trying to go, figure out how can we extend a little bit statistical physics to non-equilibrium systems. So I'm going to start with the thought that if I would write a general Langevin equation for a process, and let's assume that the noise here could be anything. So it's not only thermal noise, it could be some driven or active noise or whatever. Maybe there is no thermal bath around, but I can still write the equation. And I would like to, and this thought comes from this Kubo statement, which says that if you have a single physical process governing the noise, the fluctuations, and the dissipation in the system, then these should correspond, and why would that not happen in a system out of equilibrium? So this is where I want to go. So I'm going to start, I'm going to show you two experimental systems, and start from the fluctuation dissipation relation, or the generalized fluctuation dissipation relation, and see how far I can take the effective temperature in describing what is going on in the system. Yeah, so the effective, so when I say I'm going to take the fluctuation dissipation relation in one system, I'm actually going to do a fluctuation dissipation relation experiment, and I'm going to define an effective temperature because, of course, the regular normal fluctuation dissipation relation doesn't hold. In the other one, I'm going to just take the static relation, the Einstein relation. And again, the question would be, okay, so if I can define this, then does it really govern the thermodynamics of the system? And I'll try to show you how I watch it. So the two systems are, one is a colloidal suspension. This is a colloidal suspension that there are optical forces induced by holographic optical tweezers that add additional fluctuations to the system, and then we will ask what is happening in a diffusive contact. And the other system is a styrofoam ball that is placed in a ball and subject to noise from active hex bugs. So these are very different systems. One is microscopic, one is macroscopic, one has a heat bath, one it doesn't have. And the question is what is, and I'm going to study the same sort of question in both of these systems. To give a little bit of equal footing, I'm going to start with colloidal suspensions with no driving forces. And you're seeing here basically a few particles until until something equilibrates. And what actually has to equilibrate? So in equilibrium, we maximize entropy as a function of the internal energy to get one condition, which is equal temperatures. And then we do the same for the number of particles, and we get the second condition, Einstein relation or effective temperature.